Hey Bulldogs, we are working on chapter 3.3 today, and this lesson is actually going to be split up into two separate videos. So this first video is on something called the power rule, and there will be a follow-up video on the product rule and the quotient rule. So this is chapter 3.3.1, I'm calling this, and I'm in your notes packet on page 7. So if we were in the classroom working in groups, which we're not this year, it's a different year, but what I would actually have you guys doing is I would assign one of these problems to each of our groups, and their objective would be to evaluate the derivative using the definition number 2 of a derivative, the limit as h approaches 0 of f of x plus h minus f of x all over h. So I'm going to illustrate one of the examples. So I'm going to grab question number 3, f of x equals x squared. So this is our problem. And we are going to find the derivative. So now I'm going to call that f prime of x. That's our new notation as of yesterday's lesson, which I know is the limit as h approaches 0 of f of x plus h minus f of x all over h. And I know at this point what I want to do is compose x plus h into the f function in order to find an expression for f of x plus h. So x plus h substituted in for x would give me x plus h quantity squared. And then we have minus, this is like your front end, minus f of x, which is just x squared. And that is all over h. So I am going to expand this out and clean it up. So we have x squared plus 2xh plus h squared minus x squared all over h. So you can see my x's are going to cancel out, leaving me with only 2 terms left, and both of those terms are divisible by h. So I'm going to go ahead, just to save myself a step and conserve some space, I'm going to divide each of those terms by h. So 2xh divided by h is 2x. H squared divided by h is h. And now I'm ready to substitute in my 0. So we have f prime of x equals 2x plus 0, or f prime of x equals 2x. Okay, so I'm going to come over here, and I'm going to drop in my derivative right underneath the function. And at this point, I'm going to pause the video, and I'm going to populate the rest of these that I would have had other people in the class doing as an example. So now we have all of the problems up through example number 5. And what we are looking for today is a more efficient way to evaluate the definition of a derivative. This process is not that bad, but once you get to a problem like x to the 6th, you are expanding out x plus h to the 6th power, and we can use binomial expansion, but this becomes very long and it becomes a tedious process. And can you imagine if we were asked to find x to the 80th? No, thank you. So we are looking for maybe some patterns that are happening that can allow us to shorten up this process a little bit. So you'll notice for my very first function where I have a constant, my derivative is 0. For my function f of x equals x, my derivative is 1. For x squared, my derivative is 2x. For x cubed, my derivative is 3x squared. For x to the 4th, my derivative is 4x cubed. So let's look for some observations here. So what I'm noticing is the coefficient of 2 happens to match the power. And that is the case on this one as well. The 3 matches the original power. The 4 matches the original power. Even on the first one, the power is 1, and my coefficient is a 1. On example number 1, we could imagine that there's an imaginary x to the 0, and the power of x would match my coefficient. So that's the first thing I'm noticing, is that the power of my original function becomes the coefficient. So your power on f of x becomes the coefficient of f prime of x. And if we look at what else is happening on our problem, my power has come to the front, but my power then on the derivative drops down by 1. My x cubed drops down to x squared. My x to the 4th drops down to x cubed. So that's another observation that I am noticing, is that my power on f of x is decreased by 1 on f prime of x. So if I were to try to apply that rule to example number 6, my power on f of x, so 5, becomes the coefficient of f prime. So the 5 becomes the coefficient. And then my power drops down by 1. So that leaves me with an x to the 4th power. So if I were to try that with example number 7, my 6 becomes my new coefficient, and then my power drops down to a 5. For example number 8, my 80 comes out to the front, my power drops down to a 79. So what would happen if we had some other type of coefficient there already? So let's say we had, I'm going to put an alternate example up here. Let's say we had f of x equals 2x cubed. Oh, you can't see that. F of x equals 2x cubed. Well, if we had actually performed this calculation in here, so I would have 2 times the expansion of x plus h cubed. That 2 would carry down on the next step, it would distribute, and we would actually have a 2 left over at the end, which means if I want to find the derivative using these new patterns that I'm noticing, this 2 in the front actually just carries down. The power, the 3, does pull out to the front to become a coefficient, so those two will actually become a product of 2 coefficients to give us 6. And then my power will drop down to a 2. So the most cleaned up version of this would be 6x squared. And if we wanted to look at one more example of this, let's say we had something like f of x equals 6x to the 4th power. The 6 just carries on down. You can also remember we have a limit law that allows us to take a coefficient of a limit and pull it out to the front of the limit. So you can also consider that that's what's happening behind the scenes here. So the 6 carries down, the 4 comes out to the front as another coefficient, and my power drops down to an x cubed. So this cleans up to 24x cubed. And by all means, if you want to hop over that step and multiply 4 times 6 just to get 24, that is absolutely fine. So this is what we call the power rule. And so let's write a version of it where we have all variables. So I have a coefficient to start times a variable x raised to the power of n. So this notation here means the derivative with respect to x of c times x to the n is, so here we're going to write the derivative. So this coefficient way out in the front carries down. My power comes out to the front and also becomes another piece of my coefficient times x, and my power drops down by 1. So times x to the n minus 1. If I had just the derivative of a constant, we can look at example number 1 up here. That power rule still applies. The power behind the scenes, it's x to the 0, is 0. 0 times 7 is 0. And my power, well, at that point, it's 0 times anything. So we're looking at a 0 here. So that means the derivative of a constant is always going to be 0. All right, let's look at some examples. Now, the directions state, find f prime of x, write all final answers with positive exponents and in radical form if applicable. All right, so for example number 1, we're finding our derivative. And this is just a series of individual terms. So we're going to apply that power rule to each individual term. So I'm going to pull my 4 out to the front. So you'd have 4 times that coefficient of 3, and then my power drops down to an x cubed. My 3 comes out to the front. If you guys are okay with this, I'm just going to take this shortcut. I'm just going to multiply 3 times 2, which gives me 6. My power drops down to an x squared. When you have a power of 1, 1 times negative 3 is negative 3, and your power of 1 drops down to 0, so you don't have an x anymore. And then the derivative of plus 11 is 0, so we don't have anything. You could put a 0 on there if you want. You don't need to. And I'm just going to write one more step where I clean up that very first one. So we have 12x cubed plus 6x squared minus 3. This is significantly faster than if we had to evaluate the limit as h approaches 0 of f of x plus h minus f of x. You would be substituting x plus h in here. You'd be raising it to the 4th power, to the 3rd power, and then to the 1 power. And it would be a very long, tedious process. And we can do this one in less than a minute. All right, let's take a look at example number 2. So this is my derivative. I'm going to pull my 8 out to the front because that's a fraction. I'm not going to do that in my head. I'll just clean it up on the next step. So 8 times 3/4, my power drops down to a 7. 2 times 10 is 20. Power drops down to a 1. Negative 1 times negative 3 is positive 3. Power drops down to a negative 2. And the derivative of a constant is always 0. So when I clean this up, of course, I'm going to clean up my coefficients here. So 4 goes in 8 2 times. 2 times 3 is 6x to the 7th plus 20x. But they are wanting us to write answers with positive exponents. So what that means is I'm just going to rewrite this and move my x to the negative 2 down to the denominator. You'll recall that skill from previous math classes. Okay, let's take a look at number 3. Now my variable here is r. So I'm finding f prime of r. I'm going to multiply the 3 out to the front. So 3 times 1/3. This pi is just a constant number. It's a coefficient, so it just carries down. R is my variable, though, so that power drops down to r squared. And then my pi is a constant, so the derivative of a constant is 0. So I'm just going to clean that up. So 3 times 1/3 is 1, so we have pi r squared. Okay, as you look at example number 4, we have a radical here, and this power rule only applies when it is in the form of a coefficient times a variable raised to a power. So what I'm going to do is start by rewriting this square root of x in a rational exponent form. So I'm just going to come over to the right here. So we're going to have y equals, and I'm going to rewrite this as x to the 1/2 power. Remember, that's a power of 1 with a root of 2, plus 5x. And then I'm also going to rewrite minus 2 over x. I want this written in a base to a power form. So I'm going to push that x to the top, which means I'm now going to have minus 2x to the negative 1. Remember, when you move a variable from the top to the bottom, it just changes the sign of your power. Now I'm finding my derivative. And notation-wise, that was a y, so now I'm going to call this y prime. So the 1/2 comes to the front. My power drops down to a negative 1/2. So 1/2 minus 1 is negative 1/2. 1 times 5 is 5. My power drops down from a 1 to a 0, so I don't have an x anymore. Negative 1 times negative 2 is plus 2x, and then just be careful. You have a negative 1 dropping down by 1. So negative 1 minus 1 is going to leave us with a negative 2. And then I'm going to clean this up. Y prime equals, and I'm going to take this x to the negative 1/2. I'm going to push that into the denominator. So I have 1 over 2, and x to the 1/2 in the denominator pushes the x down, but also that's a 1/2 power, which is the same as a square root. Plus 5 plus 2 over x squared. And I'm just realizing as we are working this problem. No, we're looking good. All right, we're looking good here. Okay, there's my final answer. All right, just a reminder, we want to write positive exponents. I've got positive exponent. We want radical form. We've got radical form. All right, take a look at example number 5. So I have a square root of 2 times x, and then I have a square root of 3x. Now you need this, first of all, written in a form where, I'm going to separate this, in a form where you have a coefficient times a base to a power. Now I already have that for the first one, but I do not for the second one because these are grouped together. So I'm going to separate those out. So we're going to have square root of 3 as my coefficient, and then the square root of x would be x to the 1/2 power. And now I'll find my derivative. 1 times square root of 2 is square root of 2. Power drops down to a 0. 1/2 times square root of 3 is square root of 3 over 2. X to the negative 1/2 power. 1/2 minus 1 is negative 1/2. And now I'm just going to write one more step where I clean this up. So we have square root of 2 plus square root of 3 over 2. And because I'm going to push this down into the denominator, it's just going to join my coefficients denominator. So I'm going to have x to the 1/2, which is the same as the square root of x. Don't worry about having a radical in the denominator. When there's a variable, you can always keep a radical in the denominator. All right, we've got one more example to take a look at today. So this is example number 6. So we have y equals 1 over x squared. So the first thing I'm going to have to do is rewrite this. So that's going to be, I'm pushing my x squared up to the numerator. So that's y to the negative 2. This is actually called a rewrite, by the way, when you rewrite your original function. Minus 2, and then this 3 is part of the 2. So that is a coefficient that can stay there. It's the x that needs to be out of the denominator. So I'm pushing that x up to the numerator to become an x to the negative 1. And then I've got my 1/5. So let me emphasize that. The 2/3 is my coefficient. That stays as the coefficient. Only the x pulls up to the numerator. That way it's still in the form of a coefficient times a variable to a power. Okay, so now I'm going to come over here and find my derivative. So negative 2 comes out to the front. My power drops down. So negative 2 minus 1 is negative 3. Negative 1 times negative 2/3 is positive 2/3. Subtract your power. Negative 1 minus 1 is negative 2. And then the derivative of a constant is 0. And I'm just going to clean this up a little bit. So I'm going to push this x to the negative 3 back down to the bottom. So we have negative 2 over x cubed plus 2/3, and that x to the negative 2 comes down to the bottom also. So there is my final answer. I'm going to hold off. We're not going to do number 8, number 7, and number 8. Those are a lead-in into our product rule and our quotient rule, which is going to be in the second video today. All right, thank you so much for listening. I hope that you found that helpful. I know you will absolutely love the power rule because guess what? We no longer have to use our formal definition of a derivative. We now have a much more efficient way. Thanks for listening, Bulldogs.